see if it works. Do you think it's recording?
Hmm.
Okay. Hi guys. um, we miss you, and
Yeah.
we are excited to tell you about our delving deeper problem that we got to explore for this class. So we decided that jelly beans were just the way to go, and our problem poses to a child how many ways they could pass out 100 jelly beans to their friends. So, for example, if they had 3 friends, you could get 95 to one friend, 3 to another friend, and 2 to the other friend, which would be 95 plus 3 plus 2 is 100. So, that would be like one way to pass out all 100 jelly beans. And the problem starts out by doing it with only 10 jelly beans to like give us that visual of what each of these different ways looks like, and how there's so many different ways to even just distribute 10 jelly beans. And essentially, what we're looking at is how many ways can we write 100 as a sum of integers? And there's a lot of ways. There's a lot of ways. We really tried hard. I actually started writing out like from 100, like 99 plus 1, 98 plus 1 plus 1, 98 plus 2, and just seeing like how the first 10 numbers would turn out. Here's some of Emma's, like she did 20, and she wrote out all the different ways you could partition 20. And it was just going to be way too hard for us to write down. Like it was just going to be impossible. Almost we'd be writing forever. And Emma was looking through her proof notes, and we considered counting multi-sets, but then they overcounted the actual number, and we stumbled upon a thing called partitions, um, which was also still daunting, but is an interesting way to look at this problem.
Yeah, so those of us who are in abstract algebra have obviously heard about partitions, because we've talked about like cosets and how they partition the group and stuff like that. So then there's also partitions in terms of number theory, which is kind of similar, but a partition of an integer is a way of writing that integer as a sum of other integers. So like we said before, partitioning 100, one partition of 100 would be 95 plus 3 plus 2, because that sum equals 100. And in partitions, we don't count repetitions as two different things. So 93 plus 5 plus 2 is the same thing as 3 plus 95 plus 2.
Yep.
Whereas, like we talked about before, I had considered counting multi-sets, but in multi-sets, it double counts those things. So it was a whole mess. But then we did some research on partitions, and we did find a partition function, and we thought that was the end, and it certainly was not, because the partition function is a transcendental function, which, if you read the Delving Deeper article about like the circles that like line up together, that talked about transcendental functions, and basically they're just functions that you can't just plug a number into and like get the answer, which was not a fun time for us. So then partitions themselves have a lot of different approximation formulas using asymptotes and some other things, in general, just to like find partitions. And there are tables of like partition numbers, which luckily we were able to look at the actual tables to make sure that our answer was correct once we had solved this problem. But then a more visual way to look at partitions are what's called Young diagrams, which is what this picture is here on the right. So this Young diagram actually represents a partition of the number 5. So it's three blocks on the top, 2 blocks in the middle, and 1 block on the bottom, which represents 3 plus 2 plus 1. So for like smaller partitions, this would definitely be a reasonable way to try and find them, to write them all out. And I think it's really helpful to see them, but it's essentially the same thing as just writing all of them out like with numbers. So it wasn't a realistic way for us to attack doing 100. So
yeah, we tried to find patterns in the way that they grew also, and we just couldn't.
There were none.
There were none, but then we found it.
But then we found this generating function, which might look really complicated at first glance, but if you break it down, it starts to like make a little bit more sense. But essentially what it is it's a product of a bunch of sums. So each term holds x powers, starting with x to the 0. That's why each term has a 1 in it. And then the first term has all of the x to the power of multiples of 1. Then the next is x to the power of multiples of 2, then x of multiples of 3, so on until you get to n itself, whatever number you're trying to partition. So if you were trying to find the partitions for 4, you would go all the way up until multiples of 4. So in each term represents the number of ways to use that integer to partition in. So the first term is how many different ways you could use, or how many times you can use a 1 to partition in. So obviously, like the x term is using 1, 1 because it's x to the first. Or in the second term, the x squared is using 1, 2 because it's the first multiple of 2 power. And then you multiply all of those together to follow the basic counting principle, because each of these terms is an independent way to partition in. So when we multiply them all together and we expand that polynomial, the coefficient in front of your x to the nth term, where n is the number you're trying to partition, that coefficient is the number of ways to partition in. So if we look at an example, it might make a little bit more sense. With this example, we tried to partition 4. So you can see we have the first term is 1 plus all of the x multiples of 4, and then 1 plus all of the x multiples of 2, and then 3, and then 4. And then, so one example that we've outlined here is if you choose the x squared term from the set of multiples of 1, and chose the x squared term from the set of multiples of 2, that represents using 2 1s plus 1 2 to get 4. You could also use the x, just the x to the first term from the first set, and the x to the third term from the third set, and that would represent using 1 1 and 1 3, which would give you 4. But then obviously when you multiply all those out, you can see that our coefficient of x to the 4th is 5, and that is actually the number of ways to partition 4.
Ooh.
So then, like I said before, this is like really tedious if you wanted to try and like multiply it out by hand. Like
impossible,
even just
really.
multiplying like polynomials with like 3 terms, and anyways, it would have been a disaster. So even just doing the 4, the partitioning 4 example gives you an x to the 15th term, and that would have taken a really long time and provided for a lot of error on me and Jesse's part. No offense, Jessie, but
I like don't even know how you do that. Whatever, it's fine.
No. So we turned to some code, and anyone who took numerical analysis with me knows that MATLAB is definitely not my favorite thing in the whole world, but desperate times
it
call
helped
for desperate
in this
measures.
case.
So we used MATLAB to write our code, and you could definitely use a different coding software. In fact, if like I did this in a classroom, I wouldn't be using MATLAB. MATLAB, first of all, isn't free, and so you would, obviously the school would need to pay for the license for us to use it, whatever. And it's also not very self-explanatory. It has its own coding language, and it can be really difficult, especially as like a beginner program for students. But to save you some of the boring details, we'll just highlight some of like the important parts of our code. At the beginning, you can see that we call a function partition. That just means that when we go down to the command window to actually run it, we can just type in partition, and then where n is, we'll put whatever number we're looking to partition. And then right below that, you'll see the sims x command. That just tells MATLAB not to actually try to solve for x as it like wants to do. So this way it leaves it all in terms of x. And then we actually use 2 for loops and an if else statement. I'm not gonna lie, like for people who really code, this isn't very impressive to them, but for me, it was impressive to me. So I'm proud of it. But then at the end, you'll see that it says, I just used any random variable, so I just used R. But you'll see expand product. That's because the first time that we ran this, it left it as all of those like parentheses factors, and we didn't get a coefficient, so we needed MATLAB to expand it for us so that we could find the coefficient attached to x to the 100th.
And we did. And when the beautiful MATLAB function multiplied out all these numbers, I mean, you have numbers all the way up to 100 and then so many after 100 too. But the coefficient in front of x to the 100th power is 190,569,292, which means that there is that many ways to partition 100 or distribute 100 jelly beans.
Like,
friends.
Imagine if we had done it by hand.
Like, we would have been writing the whole week.
Forever.
Like, I just...
we would still be doing it
It'd still
right
be
now.
running.
So
And there'd be human error
thank God
too,
for
so we would
MATLAB.
probably have had to start over multiple times. So that's the climax of our problem, is that one number. Beautiful. Using this in secondary math. So I think the only way that you would want to use this function is in a connection to something in the real world. So students would have a draw into wanting to explore such a bizarre function and something that would take them so much time. But so some examples of this discrete math in the world are in cryptography, which I think students would find super interesting, as well as algorithms that like Spotify and Netflix use to like show you things that you might like to watch or listen to. However, in current high school math classrooms, and we talked about this in our paper, there isn't a specific Common Core standard that directly requires something like this to be taught or encourages students to know this. However, there are like conversations that are being brought up as to its relevance and importance in the classroom for students and how that might be an interesting thing. So it might start coming into classrooms. And so some examples of ways that we could incorporate that might be like incorporating a coding class and working with them to bring coding into the math classroom, doing just like discrete math units like sprinkled in, or maybe just like one to introduce it to your students and see how it goes. This could be posed as a rich task for students who might be interested in exploring partitions. It could also like introduce topics like approximation and recursive functions, and Young diagrams might be interesting to them and be a visual way to see math, so that might be interesting as well. But also this could just be used as like a coding task, and lots of students are going to be interested in that, so that just might be a draw for them to be more engaged in math in general. In my personal experience, I have not encountered anything like this in high school. I don't think it would be impossible, and I don't think that students would be turned off by it. I just think it's really daunting and large, and it might be a cool way to get students engaged who are interested in coding in the math classroom, or like push your students a little bit, give them something like fun to work with on an extra day. But I just don't know if high schoolers, much less middle schoolers, but I know we're talking about high schoolers, would be super interested in delving into this, and if you took it out of a context of like coding or cryptology or something like that.
Yeah. I personally, like, maybe in, for lack of a better word, like a normal math classroom, might use this as like a rich task type of thing, like we mentioned, having students explore partitions, because some students might think of like just saying like, you know what, I found this approximation formula and it seems pretty accurate, so we're going to go with that. Other students might really be visual learners and choose to draw out Young diagrams. But I, in high school, did take a pre-engineering class, because as like somebody who was pretty good at math in high school, everybody was like, you should be an engineer. And then I took the class and was like, I really don't want to be an engineer. But the class itself was super cool. We did a lot of hands-on activities, and one of them, in our culminating project, we got to choose what we did. And so I worked with a group, and we actually created a video game simulation of like our school, and like I got to 3D model like our cafeteria and everything in it. It was super cool, and like I'll never forget that. And we used this website called Codecademy, which is free, to learn how to code. And so I learned how to code in JavaScript and coded a video game. And I don't play video games. I had never thought that I would ever code a video game. I probably will never code another video game, but it was super cool. And it's like this great memory that I have. So I think if I taught a class like that, some kind of STEM problem solving type of class, then maybe I would use an activity like this to connect some like more like textbooky math type of things to coding. But in that case, I would probably give them the function that we used and say like, hey, we've been studying for loops and if else statements, try and write an algorithm to partition these numbers. But I just I don't know that I see a direct application of this problem in an ordinary like algebra 2 type of classroom.